This is video 2 of the final module on the course on linear algebra. Here I'm going to describe a very famous procedure for producing orthonormal bases given an inner product space. So what we are going to do is we are going to explicitly construct a orthonormal basis starting with any old basis. What we are going to do is I'm going to prove something stronger. I'm going to prove the following theorem, which is sort of an extension of the basis extension theorem that you have already studied in just the context of a vector space, not an inner product space. So the theorem is as follows. Let V be Rn or Cn equipped with an inner product. Let W be a proper subspace of V. So we do not allow W to be just the zero subspace. We do not allow W to be equal to V. Okay. And let W1 to Wm be a basis of W. So start with a basis of W such that each norm Wi equal to 1. That means these Wi's are unit vectors. And Wi is orthogonal to Wj when I is not equal to j. That means we are starting with an orthonormal basis for this vector space W. Then we can find vectors Wm plus 1 to Wn such that W1 to Wn is an orthonormal basis for V. So starting with any old orthonormal basis for a proper subspace, we can keep adding vectors to it to get an orthonormal basis for V. So this is exactly like the basis extension theorem that you have studied and used in many ways. Let's see how this construction is actually done. It's an explicit construction. It's not just going to show that there is a basis. The basis extension theorem that we have already studied just shows that there is a basis. So what we do is we first use the basis extension theorem to extend it to a basis. So this particular step is not really constructive. You just extend it to a basis. What the idea is, we are going to make each one of these VI's orthogonal to all the vectors preceding it. How we are going to do that is we are going to take this Vi, let's say Vm plus 1, and subtract away its components along the previous vectors. So recall that any vector can be decomposed as a sum of two vectors, one along the given vector and one orthogonal to the given vector. So what we are going to do is we are going to subtract away the components of this vector Vi along all the preceding vectors. So what you will be left with, intuitively at least, is a vector that is orthogonal to all the preceding vectors. That's the basic idea. So let's begin. More precisely, we define Wm plus 1 prime to be Vm plus 1 minus inner product of Vm plus 1 W1 W1. Why are we subtracting Vm plus 1 W1 W1? Because this Vm plus 1 W1 W1, if you recall, is the component of Vm plus 1 along W1, and this formula is correct because W1 is a unit vector. In general, you will have a term like this, mod W1 squared, but that term is not there because W1 is a unit vector. So we subtract away all the components of Vm plus 1 along W1 to Wm. Okay, so we have defined this W prime m plus 1. We have to show that W prime m plus 1 is orthogonal to W1 to Wm. Intuitively, we know that it's going to be orthogonal, but we have to check it mathematically. So you take inner product of W prime m plus 1 with W1. That is just Vm plus 1 W1 inner product, obviously, minus Vm plus 1 W1. Why is that the case? Well, all these other terms, when you take for instance, let's take the final term, Vm plus 1 Wm inner product Wm. When you take this term, the first thing comes out and you are left with Wm inner product Wm, which is this is second slot is not Wm, this is W1. You will be left with Wm inner product W1, which is 0 because W1 to Wm is an orthonormal set. The only term that will survive is the very first term, which is Vm plus 1 W1 inner product W1 which will be just Vm plus 1 W1 1, because W1 inner product W1 is just 1. So that's why we have this left, Vm plus 1 W1 minus Vm plus 1 W1, which is just 0. There was nothing very special about W1. We could have repeated the same argument for W2, W3 dot 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 Wm, and this shows that W prime of m plus 1 is orthogonal to all the preceding vectors W1 to Wm. Okay, now we have to set Wm plus 1 to be equal to W prime m plus 1 by norm of W prime m plus 1 to make sure that this becomes a unit vector. Once you do this, this will become a unit vector. I'm going to leave a question for you to ponder over and figure out, why is W prime m plus 1 not equal to 0? We subtracted away a lot of components. It could happen that nothing is left, but that will not happen. Think about why. In fact, the next statement I'm about to write is going to actually give you the key, and I want you to think about both these statements. The span of W1 to Wm plus 1 and the span of W1 to Wm Vm plus 1 are exactly the same. Okay, that's essentially the reason W prime m plus 1 is not 0. Think about these two statements. Why is W prime m plus 1 not 0? Why is these spans not changing? So what we have done is, we have cooked up a vector Wm plus 1 such that W1 to Wm plus 1 is in fact an orthogonal set of unit vectors, and the span of this is the same as span of W1 to Wm and Vm plus 1. Okay, now we repeat the same argument with Vm plus 2. Okay, what we do is Vm plus 2, we will make it orthogonal to W1 to Wm plus 1. We will make it orthogonal to W1 to Wm plus 1 by the same Gram Schmidt procedure. And we will get a vector Wm plus 2, which is a unit vector and which is orthogonal to all the preceding vectors W1 to Wm plus 1, and span of W1 to Wm plus 2 will be the same as span of W1 to Wm, V1 and V2. Now if you keep repeating this procedure, we will finally end up with a list of vectors W1 to Wn that forms an orthonormal basis. So this is the Gram Schmidt construction. Let's see a concrete example of the Gram Schmidt procedure to make sure we understand what exactly is going on. Let's start with two vectors, V1 which is 1 1 0 and V2 which is 2 2 1 in R3. You can check that the list V1 comma V2 is actually linearly independent. Now what we are going to do is, we are going to first make V1 and V2 orthogonal and unit vectors, and we are going to produce a basis starting with V1 to V2, V1 V2. What we first do is, we make V1 a unit vector by dividing by norm of V1. Norm of V1 is easily seen to be root 2. So we define E1 to be 1 by root 2, 1 1 0. Okay. Now what we are going to do is, we are going to make V2 orthogonal to V1 by subtracting away its component along E1. So we do V2 minus V2 E1 E1, which is just the component orthogonal to E1, and divide by the norm of this. So we get a unit vector E2. Okay. So the inner product of V2 with E1, let's just compute that first because we needed to compute this entire thing. Inner product of V2 plus E1 is just 1 by root 2, inner product 1 1 0 2 1 1, which is easily seen to be 3 by root 2. Okay. So when you do the computation, when you do U2 is equal to V2 minus inner product V2 E1 E1, you get 2 1 1 minus 3 by 2 1 1 0, which is just half 1 minus 1 2. Okay. So you get U2. Now we'll have to make this a unit vector by dividing by norm U2, and norm U2 is just 1 by 4 into 1 plus 1 plus 4, which is root 6 by 2. Okay. So normalizing this vector, we obtain E2 to be 1 by root 6, 1 minus 1, 2. Okay. So we have found a list of vectors E1 and E2 which are orthonormal and have the same span as V1, V2. So by this Gram Schmidt procedure, what we have done is, given this basis vectors V1 and V2, This is a basis for some subspace of R3. We have made it into an orthonormal basis by constructing this E1 and E2. Now if you want to make this into a basis of R3, all you have to do is find another vector V3 such that E1, E2, V3 span R3. Then apply the same procedure again to make V3 orthogonal to E1 and E2, then normalize that V3. That's it. So this is a straightforward computation. There is nothing really involved in this. So this concludes the second video on the Gram Schmidt orthogonalization procedure.